Superposition principle for forces, which means what is the net force or the total force acting at a point due to the system of charges we need to find. In an electric field, if we place a charge, what is the force experienced by that charge is electric field. By taking the vector sum of all the electric fields due to individual charges according to superposition principle. Hello everyone, welcome to session 3 of chapter 1 Electric Charges and Fields. This is Swati from Department of Physics, Vidhyaashram University College, the Temple of Excellence, Mysuru. In the last class, we were discussing about the properties of electric charges, the basic law of electric charges, that is Coulombs Law. So let us now study Coulombs Law in vector form. How to represent this Coulombs Law in vector form? We all know that Coulombs Law states that the force between two charges is directly proportional to the product of magnitude of two charges, and it is inversely proportional to the square of distance between them. Now, in vector form, how to represent it? So, here you can observe the diagram. I have two charges Q1 and Q2 which are separated by a distance, and O is the origin, R1 is the position vector. From origin we have to denote position vector is always calculated or observed from the origin. So R1 is the position vector for charge Q1, R2 is the position vector for charge Q2. And F12 is nothing but the force acting on one charge due to another charge, and here also F is force acting on this charge due to another charge. So this is the basic understanding of the diagrammatic representation. So from this diagram, as I said, R1 is the position vector of Q1 and R2 is the position vector of Q2. So F12 is the force on Q1 due to Q2, because two forces, they are separated by a distance, which means one charge is feeling force due to the another charge. So here Q1 on Q1, Q2 is acting some force. So because of Q2, there is some force acting on Q1. So that is represented by F12, and F21 is nothing but force acting on Q2 due to Q1. So that is F21. Here Q1 and Q2 are nothing but the point charges. What is R21? It is nothing but the vector leading from 1 to 2, charge 1 to 2, and R12 is nothing but converse of that, that is vector leading from 2 to 1. Now this seems to be a triangle. So from triangular law of vector addition, we know the triangular law of vector addition on two sides of a triangle of equal in magnitude, then the resultant is represented by the third side of a triangle. So from this triangle we can say R21, the direction is this way, which is equal to R2 minus R1. You can see here, because we can write R1 plus R21 is equal to R2 according to triangular law of vector addition. So now we need R21. So R21 is equal to R2. Take this to the other side, it will be minus R1. So we get R21 is equal to R2 minus R1. And similarly, we can write same for R12, which is equal to R1 plus R2. From triangular law of vector addition, we get the expressions for or the equations for R21 and R12. Now, force on Q2 due to Q1. We have to write Coulombs law between these two charges, that is F21 is equal to, according to Coulombs law, it is 1 by 4 pi epsilon naught. What are the two charges? Q1 and Q2 divided by the distance between them, that is R21 square into the unit vector R21 cap. So what is unit vector? I have told you in the last class, which gives the direction of unit vector, always represents the direction. Similarly, we can write the expression for F12, that is 1 by 4 pi epsilon naught Q1 Q2 divided by R12 square into R12 cap. Here R21 and R12 are nothing but the vectors which are leading from one point to another point. So now from these two expressions, look at the previous expression. Here we got R12 as R1 plus R2 and R21 as R2 minus R1. So from this we can write R12 is equal to minus R21, and hence we can write F12 is equal to minus of F21. So Coulombs law agrees with Newton's third law. For every action there is equal and opposite reaction. Suppose if these two charges are of same charges, say for example, they can both be positive or both be negative. But what if they are of opposite sign? If they are of opposite sign, there must be a force of attraction between the two charges, and diagrammatically we can show F12 and F21 in this way. So this is about Coulombs law in vector form. We can even show how the Coulombs law agrees with Newton's third law of motion. So let us now move on to the superposition principle for forces. Superposition principle for forces, which means what is the net force or the total force acting at a point due to the system of charges we need to find. Say force on any charge due to a number of other charges is equal to the vector sum of all the forces that acting at one point due to n number of charges, which means we need to take the sum of all the forces due to other charges at that point to find the force at that point. So that is the definition for the superposition principle of forces. The individual forces are unaffected due to the presence of other charges. No force will be affected due to the presence of n number of charges. So it's basically in a system of charge, if we are finding the total force at one point, it is the sum of the forces acting at that point due to the individual charges. Let us learn how to write the expression or how to understand this in a better way. So we have taken n number of charges. You can observe here Q1, Q2, Q3. These are the charges, and corresponding R1, R2, R3 are the position vectors. From the origin, the position vector to be denoted. So R1, R2, R3 are the position vectors. So we have Q1, Q2, Q3 are the system of three charges, and the force on Q1 due to Q2, see here, force on Q1 due to Q2 due to Q3 are obtained by the vector addition of forces due to each one of these charges. That is the superposition principle. Now let us now find what is the force on Q1 due to Q2, what is the force on Q1 due to Q3. So for that we need to apply Coulombs law. So F12 suggests, what is the meaning of F12? Force on Q1 due to Q2. 1, 2 represents force on Q1 due to Q2, which is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by, what is the distance of separation between them? It is R12. R12 is the distance of separation, and R12 cap is a unit vector. So we can write R12 square into R12 cap. Similarly, force on Q1 due to Q3, since it is the force on Q1 due to Q3, it is F13. Since it is a vector, we need to write the arrow mark on top, which is equal to 1 by 4 pi epsilon naught Q1 Q3 divided by R13 square into R13 cap, because R13 is distance of separation between Q1 and Q3, and R13 cap is the unit vector which gives the direction. So the total force, how to calculate the total force here at this point? This point Q2 and Q3 are also giving some force to this point Q1. What is the total force on this point Q1? That can be calculated by taking the vector sum of all the forces at that point. So F1 is equal to F12 plus F13. Now what is F12? According to this, it is 1 by 4 pi epsilon naught Q1 Q2 divided by R12 square into R12 cap, plus F13 is 1 by 4 pi epsilon naught Q1 into Q3 divided by R13 square into R13 cap. Now look at this expression. Can we take anything outside? What are the common terms that we have? So here we have 1 by 4 pi epsilon naught Q1, 1 by 4 pi epsilon naught Q1. So these are the common things. So we can take outside. So 1 by 4 pi epsilon naught Q1 Q2 divided by R12 square into R12 cap, plus Q1 Q3 divided by R13 square R13 cap. These are the two charges which is taken for our example, and if we write it for n number of charges, it will go up to so on, and it is Q1 Qn divided by R1n square into R1n cap. That is for n number of charges if we consider. So now we can write it as F1 is equal to, taking Q1 outside, Q1 divided by 4 pi epsilon naught. Since it is plus sign between all the terms, we can write it as summation of I to n Qi divided by R1 I square into R1 I cap, which means we can substitute I value from I to n number of values. So summation indicates it is the sum of individuals. Here in this case R12, R13 and up to so on up to R1n are unit vectors which indicates the direction. So this is the superposition principle for system of forces. So far we have studied about the electric charges, their characteristics, their properties, the laws which signifies electric charges. And now we are moving on to the another important topic, that is electric field. What is the meaning of electric field? What is the basic difference between electric charge and field? Let us learn. So electric field due to a charge at any point in space is defined as the force experienced by unit positive charge. Electric field is nothing but the force experienced by unit positive charge if placed at any point. In an electric field, if we place a charge, what is the force experienced by that charge is electric field. And it is given by the expression E is equal to F divided by Q. So electric field is a vector quantity and hence it should be denoted with the arrow mark. So in this expression, E is electric field, F is the force and Q is the charge. Basically, the force experienced by unit charge is electric field, which is very important and easy to remember the definition. Now, what are the basic things which we have to know about electric fields? As I said, it is a vector quantity. What is the SI unit for electric field? Look at this expression. We have F divided by Q. What is F? It is force. What is the SI unit for force? Newton. What is the SI unit for charge? Coulomb. So we can write it as Newton per Coulomb, that is the SI unit, or we can also say it as volt per meter. So here in the study of electric field, we must know about two important terms, that is the source charge and the test charge. So what is the source charge? The charge which produces the electric field is said to be a source charge. The name itself defines. Source of electric field is source charge, which means charge which produces the electric field. What is test charge? So it will not produce electric field. A charge which tests the effect of source charge is called as test charge. So this is about basic thing regarding electric field. Let us now find electric intensity due to a point charge. What is the intensity? What is the electric intensity due to a point charge? Let us see now. See here, we have taken Q plus Q. So capital Q, that is charge placed in free space at this point O. So here plus Q is unit positive charge which is there at a position P. So now what is the distance of separation between these two charges? That is R. So electric field, we are finding the electric intensity. But what is electric field? It is defined as E is equal to F by Q, as we have studied in the previous slide. So in this expression, E is electric field and F is the force exerted by a charge and Q is nothing but a point charge which is there at a position P. Now there are two charges, there is a distance of separation, there must be a force between these two charges. Then according to Coulombs law, it is F is equal to 1 by 4 pi epsilon naught Q, capital Q and small q divided by R square into R cap. Because these two are the charges separated by distance R, hence we can write Coulombs law as 1 by 4 pi epsilon naught Q into Q divided by R square into R cap. Now substitute F in this equation. E is equal to F divided by Q. So let us now substitute E is equal to, in the place of F I am writing the same. That is 1 by 4 pi epsilon naught Q into Q divided by R square divided by Q, and here we have R cap. Now we can cancel Q and Q because they are same. So, and we remain with E is equal to 1 by 4 pi epsilon naught Q divided by R square into R cap. This is the vector form of electric intensity due to a point charge. So, next we are moving on to electric field lines, which is very important to understand. So, what is an electric field lines? An electric field line is a path in electric field. It may be straight or curved such that tangent drawn at any point gives the direction of electric field intensity at that point. See, you can observe it is starting from positive charge and ending at negative charge. It is a curved path, it can even be straight path, and if we write tangent at any point, that gives the intensity of electric field at that point. So the direction of electric field should be from always positive to negative. That is very important. So the electric field around some simple charge configuration, let us now see. Here I have taken a positive point charge, and in positive point charge the electric field are always directed outwards radially. You can observe the arrow mark here, which is radially outwards due to a positive point charge. In case of negative point charge, it is radially inwards. You can observe the arrow mark. It is radially inwards. What if you take a dipole? So if you consider a dipole is nothing but a pair of equal and opposite charges separated by a distance in an electric field. So plus and minus, this is the dipole, and in this case you can observe from positive it is moving and terminating at negative. From positive and terminating at negative. From positive charge, if you observe, it is radially outwards, and for negative charge, if you observe, it is radially inwards. So this is how electric field lines are drawn due to a pair of equal and opposite charges, that is a dipole. And consider here positive charge, you can observe electric field lines, they are radially outwards everywhere, and if you continue this curve and it is outwards, and while going to negative charge it should be inwards. This is how the direction of electric field lines must be. And next we have 2 point charges which are of same kind, that is 2 positive charges. We can see now here the electric field lines are directed outwards from positive charge in both the case. Similarly, we can write it for negative charges. You can find they are moving inwards. So since they are minus q and minus q, in both the conditions we can observe the direction is inward. So from this we can understand that at equal distances from charge at equal distances, the magnitude of its electric field is always same. You can observe here these are radially outwards but which are of equal distance, and now from this point to all these distances the magnitude of electric field is always same. So this is one of the special condition we must know about. So in the next session we will learn some more interesting concepts. Until then, keep learning all of you. See you all in the next session. Thank you.